In many situations, we're interested in determining the number of ways we can permute in distinct objects taken r at a time, where r is some value less than n. What that means in layman's terms is that we want to arrange some of the objects we're given, but possibly not all of them. So what if we begin with the same 5 people from number 3 that we did just a second ago, but we only want to seat 2 of them in a row? How many ways are there to do this? So we already took 5 people and seated all 5 of them in a row, and we saw that that was 5 factorial, 120 ways. But what if we start with that same n of 5 people and we only want to seat 2 of them? Okay, so there would be 5 choices for that first person, right? There are 5 people standing there and I say, I choose you. So I take that first person, there are 5 choices for who that first person is. And then I need to pick one other person out of the 4 who are left. So there are 4 choices for the next person. And unfortunately, the other 3 people just have to leave. They don't get a seat at all. Well, that's only 20 different ways. So notice how that really reduced the options there if I only want to seat 2 of them rather than all of them. So this leads us to our next definition for permutations, which is if I want to permutate indistinct objects r at a time, this is given by a formula. We say this as like n choose r permutation, and we can calculate that by doing n factorial over the quantity n minus 1 factorial. There's also a way to do this in your calculator. The permutation option is under the math probability menu, and it's option number 2. Okay, so just to see how these work, if I want to permutate 6 objects 6 at a time, this is actually back to that first definition. We know this should end up being 6 factorial based on our first set of notes. But let's see how it works with this formula. So both n and r in this case happen to be both 6. So this would say to do 6 factorial over the quantity 6 minus 6 factorial, or 6 factorial over 0 factorial. But we've been defined that 0 factorial is just 1. So 6 factorial over 1 is the same as just regular 6 factorial. So I can just do 6 math over to probability, pick my factorial, and that's 720. Okay, what about if I want to permutate 6 objects 4 at a time? Using my definition, this would be 6 factorial over the quantity 6 minus 4 factorial, or 6 factorial over 2 factorial. And maybe I want to just do this without going into my calculator. 6 times 5 times 4 times 3 times 2 times 1 on top, 2 times 1 on the bottom. Cancel those out. So basically, I'm doing 6 factorial, except I'm not multiplying that very last 2 in there. This should end up being 360. To see how one of those would work in your calculator, you do have to plan ahead. You have to know what you're doing first. So let's do the permutation of 6 4 at a time. You have to hit 6 first, because that's the first value in here. And then you can go to math and over to probability, choose option 2 for permutation, then you can type in your 4 and hit enter and get that 360 out. But I always forget to plan ahead. I always go into the menu and then I realize I have to come back out. Okay, so find the number of permutations that can be formed of all the letters in the name Bob. Notice in this case that all the letters are distinct. We can tell them apart because one is a capital B and one is a lowercase b. So I can actually tell those apart. Okay, so I have in this case a permutation that I want to do of 3 different letters, 3 different objects, and I want to permutate all 3 of them. So by definition, we know that this should be 3 factorial, which is 3 times 2 times 1, which is 6. And just because, to double check that, let's try writing them out. We know capital B, O, B is 1. Then we could do capital B first again and reverse the other letters. Then we could start with O and do the two different arrangements of the B's. And finally, we could start with the little b and arrange the other letters behind that. So there would be our 6 different arrangements. Then it says, find the number of permutations that can be formed from the letters of the word lowercase b-o-b, Bob. Notice in this case, the letters are not distinct. We cannot tell them apart. Okay, well, this falls not into our original category. I'm going back up to the original. When we defined a permutation, it says you can tell all the objects apart. So all of a sudden we have a kink in this, in that what do we do if we cannot tell them apart? So we don't know a formula for this yet. Let's just try writing them out together. I could do as written, lowercase b, o-b. I could do the b's first and then the o. I could do the o first and then the 2 b's. And that's it. If you try rearranging those any other way, you're going to get something that you've already got. So there are only 3 ways to do this whenever we have not distinct. So what this leads us to is, okay, well, what is our rule then if we want to permutate in objects that are not all distinct? So what you can see is that if you've got objects that are like, they're not all distinct, but you have certain ones that are alike, what you end up having to do is do your n factorial over, and then on the bottom in the denominator, you do different factorials for however many are the same. Okay, so how would this formula, how would this work up here? What it would end up saying is I'm going to do 3 factorial on the top because I have 3 total letters that I want to permutate. But on the bottom, I would do 2 factorial for the little b's because there are 2 of those that are the same. And I would do 1 factorial for the little o because I only have 1 of those. So you can see I would get 3 times 2 times 1 over 2 times 1 times 1. The 2's would cancel out, and that's how we would arrive at just a 3. So let's apply that to another problem. Find the number of permutations that can be formed from all of the letters in the word Mississippi. Okay, so definitely we have some non-distinct objects, so we know we're going to have to use this non-distinct formula. And we have, if you count up the letters in Mississippi, there are 11 total letters. So if I apply this formula, I'm going to have 11 factorial on the top. And then on the bottom, I have to multiply together all the factorials for the different objects. So if we look at this, I'm going to start with the s's. There are 4 s's, which means we have to do a 4 factorial on the bottom for those. There are also 4 i's, so we need another 4 factorial on the bottom for those. There are 2 p's, so I need a 2 factorial down there for those. And there is 1 m, so we need a 1 factorial for that. So again, I could go into my calculator and try to do all of these. I find that to be a little bit harder than just writing it out. So I'm going to write out expand 11 factorial on the top. I know it's long. And then on the bottom, I'm going to expand these. I'm going to do 4 times 3 times 2 times 1 times 4 times 3 times 2 times 1 times 2 times 1 times 1. Okay, so I'm going to go through and cancel these out. It looks like this 4, 3, 2, 1 can cancel out with a 4, 3, 2, 1 down here. And then we've got some other canceling we can do. Let's see, this 4 and this 2 together could cancel out that 8. And then maybe I would like to cancel this 2 and this 3 in the denominator with the 6 that's on the top. And we've run out of things to cancel in the denominator. Everything down there is now just a 1. And what we have left in the top is 11 times 10 times 9 times 7 times 5. So that's what I really need to figure out. So I'm going to do in my calculator 11 times 10 times 9 times 7 times 5. And it looks like 34,650 ways, distinct ways to permutate the letters in the word Mississippi. How many different signals can be made by hoisting 2 yellow flags, 4 green flags, and 3 red flags on a ship's mast at the same time? Okay, so again, if I add this up, I've got 2, 3, 4, 5, 6, 7, 8, 9 total flags. But I've got these ones that are of the same type. So we would do 9 factorial on the top, a 2 factorial, 4 factorial, and 3 factorial on the bottom. And I'm just going to expand these again. So expand 9 factorial on top, and then 2 times 1 times 4 times 3 times 2 times 1 times 3 times 2 times 1 on the bottom. And start canceling things out. So I see I can cancel 3s, 2s, 1s. Here's a 4 that can cancel. Here is a 3 and a 2 that can cancel with a 6. And maybe I can cancel this 2 with the 8 on the top and make that 8 a 4. And then that looks like I've exhausted everything in the denominator, leaving me on top a 9, a 4, a 7, and a 5. So that's when I'm going to choose to go to my calculator. 9 times 4 times 7 times 5. And I get 1,260. So when you're doing these for me, I want to see at very minimum this first setup where you show me that you're using this formula and you set up the different factorials. It's also even a good idea to write what they stand for under here. So maybe I put a Y for the yellows, a G for the greens, and an R for the reds. And then how much you expand from there is your choice, working down to the final answer. Again, you're welcome at that point to do 11 factorial totally in your calculator. Again, I personally just feel like it takes me more time to do that than to just write it out and figure it out.